Okay, let's get into it. Number 14, Olbers Paradox. Go outside tonight and look up, and you'll see something so ordinary you've never questioned it. The sky is dark. Between the stars, there's black. And that black should not be there. Here's the reasoning. Imagine the universe is infinite, unchanging, and filled evenly with stars in every direction. Now pick any point in the night sky and look straight out along that line. If space goes on forever with stars scattered all through it, then sooner or later that line has to land on the surface of a star. Maybe a near one, maybe one unimaginably far away, but it lands on one eventually. And that's true for every single line you could draw. Every direction ends on a star, which means the entire sky, top to bottom, horizon to horizon, should be a solid wall of starlight, as bright as the surface of the sun. Night should not exist. A German astronomer named Heinrich Olbers laid this out cleanly in 1823, though the puzzle had been nagging people for centuries before him. Olbers guessed the answer was dust, clouds of it soaking up the light from the faraway stars. But that doesn't work. Anything absorbing that much starlight would heat up and start glowing just as brightly. You can't hide from an infinite sky. And here's the part that gets me. The man who got closest to the real answer wasn't a scientist at all. It was Edgar Allan Poe. In 1848, in a strange, sprawling prose poem called Eureka, Poe suggested that the reason the sky is dark is that the light from the most distant stars simply hasn't arrived yet. The universe hasn't been around long enough. He was right. The universe is not infinitely old. It's about 13.8 billion years old, and it's expanding, stretching the light from the farthest galaxies until it fades out of view entirely. So when you look up and see darkness, you're not seeing empty space. You're seeing the edge of time. You're seeing back to before there were any stars to shine. The dark between the stars isn't nothing. It's the oldest thing you will ever look at. It's the universe telling you, quietly, every single night, that it had a beginning. And most of us walk right under it without ever looking twice. Number 13, the twin paradox. Take two twins. Same birthday, same everything. One of them climbs into a spacecraft and flies off toward a distant star at almost the speed of light, then turns around and comes home. The other one stays on Earth, waters the plants, gets older. When the traveler lands and steps out, the twins are no longer the same age. The one who flew might have aged 2 years. The one who stayed home has aged 40. They were born on the same day, and now one is middle-aged and one is barely out of their 20s. This isn't a story. This is how the universe actually works. A physicist named Paul Langevin spelled it out in 1911, building on Einstein's discovery that time is not a fixed, universal thing ticking at the same rate for everyone. The faster you move through space, the slower you move through time. Get close enough to the speed of light, and time for you slows to a crawl compared to everyone you left behind. Now, the reason it's called a paradox is this. Motion is supposed to be relative. From the traveler's point of view, they're sitting still, and it's the Earth that flew away and came back. So shouldn't each twin see the other as the younger one? Who actually ends up older? The answer is the traveler ends up younger, and the tie breaks because their journey isn't symmetric. The one who leaves has to accelerate, slow down, turn around, and come back. They feel those forces. The earthbound twin never does. That turnaround is real, and it's what settles the difference. And here's the thing. We have tested this. In October of 1971, two scientists named Haffel and Keating took a set of atomic clocks, accurate to billionths of a second, and flew them around the world on ordinary commercial airliners. Then they compared those clocks to identical ones that stayed on the ground. The flying clocks disagreed, by exactly the amount the math predicted. It's not a thought experiment. Right now, the satellites in orbit above you are ticking at a slightly different rate than your watch, and the GPS in your phone has to correct for it constantly. If it didn't, your navigation would drift miles off within a day. Time is not the steady drumbeat you thought it was. It bends, it stretches, and whether you age faster or slower than the people you love depends just a little on how fast you're moving. Number 12. The ladder paradox. Picture a ladder that's too long to fit inside a barn. Say the ladder is 20 feet and the barn is 15. Obviously, it doesn't fit. You've known this since you were a kid. Now carry that ladder at almost the speed of light, straight through the barn, in one open door and out the other. Something bizarre happens. When objects move that fast, they contract along the direction they're moving. It's called length contraction, and like time slowing down, it's a real, measured effect. So from the barn's point of view, that 20-foot ladder squashes down, shrinks to maybe 10 feet, and for one brief instant, the whole thing is entirely inside the barn. You could, in principle, slam both doors shut with the ladder fully contained. But now, climb onto the ladder and see it from there. From the ladder's point of view, it's not moving. The barn is. And so it's the barn that contracts, shrinking from 15 feet down to maybe 8. From up on the ladder, the barn is now much too small, and there is no moment, none, when the ladder fits inside. So which is it? Does the ladder fit in the barn, or doesn't it? And the answer that should make the back of your neck prickle, is that both are true. There is no single fact of the matter. The escape hatch is a thing called the relativity of simultaneity. When the barn's frame says both doors are shut at the same time, the ladder's frame does not agree that those two door closings happen at the same time. From the ladder, the far door opens and lets the front end out before the near door ever closes behind the back end. Nothing gets crushed. Both stories are perfectly consistent. They just don't agree on what happened when. Sit with that. Two events, the front door and the back door, happen at the same moment for one observer and in a clear sequence for another. And neither of them is wrong. We like to think there's one true timeline, one master clock, one universe where things happen in an order everyone agrees on. There isn't. At the same time is not a fact about the universe. It's a fact about you and how you're moving. The word now is smaller than you think. Number 11. Schrödinger's cat. You've heard the name. A cat, a box, alive and dead at the same time. But the story behind it is stranger than the slogan, because the man who came up with it was trying to prove that the whole idea was ridiculous. Here's the setup. Put a cat in a sealed steel box. Inside, a single radioactive atom, a tiny hammer, and a vial of poison. If the atom decays, the hammer falls, the vial breaks, the cat dies. If the atom doesn't decay, the cat lives. Now, quantum mechanics tells us something deeply weird about that atom. Until it's measured, it isn't in one state or the other. It's in a blur of both at once, decayed and not decayed, layered on top of each other. Physicists call it superposition, and for tiny particles, it's not philosophy. It's experimentally real. But the cat's life is wired directly to that atom. So if the atom is genuinely both decayed and not, then the cat, following the same logic, is both alive and dead. Not, we don't know which. Actually both. At the same time. Until someone opens the box and looks, and reality picks one. Erwin Schrödinger cooked this up in 1935, and he wasn't celebrating quantum mechanics. He was mocking it. He thought a living animal smeared across life and death was so obviously absurd that it revealed something broken in how we understood the theory. He called these ridiculous cases. The joke is on him, because in the decades since, physicists have taken larger and larger objects, molecules, then bigger molecules, and coaxed them into genuine superpositions in the lab. The line between tiny quantum weirdness and the everyday world where cats are just alive or just dead keeps getting pushed further out. Nobody has done it to an actual cat, and probably nobody ever will. But the wall Schrödinger assumed was there, the wall between the quantum and the real, has never actually been found. And that's the unsettling core of it. We know quantum superposition is real. We know it applies to atoms. And we do not have a clean, agreed-upon answer for why it seems to stop applying by the time you get up to the scale of a cat, or a person, or you. Schrödinger built his cat to kill an idea. Instead, the cat got out, and it's still in the box, and out of it, waiting for someone to explain why the universe is allowed to be two things at once. Number 10. Maxwell's demon. The second law of thermodynamics is about as close to sacred as physics gets. It says, roughly, that things fall apart. Heat spreads out, order decays, and the total disorder of the universe, what we call entropy, only ever increases. You can't unscramble an egg. You can't make a cold room heat up on its own. In 1867, a Scottish genius named James Clerk Maxwell invented a little creature whose only job was to break that law. Picture a box of gas, split into two halves by a wall with a tiny trapdoor. The gas is the same temperature throughout, which really means it's a mix of fast molecules and slow ones bouncing around everywhere. Now station a tiny, intelligent being at that trapdoor. Every time a fast molecule comes flying toward it from the left, the demon opens the door and lets it through to the right. Every time a slow one approaches from the right, it lets that through to the left. It's not pushing anything. It's just opening and closing a weightless door at the right moments. But over time, all the fast molecules pile up on one side and all the slow ones on the other. One side gets hot, the other gets cold. Order appears out of an even, lukewarm mush. Entropy goes down. And you could run an engine off that temperature difference for free, forever. That's a disaster. A machine that violates the second law would break physics wide open. So where's the catch? It took almost a century to nail it down, and the answer is one of the most beautiful ideas in science. The catch is memory. To sort the molecules, the demon has to know which ones are fast and which are slow. It has to measure them, and remember, at least for a moment, what it saw. And its memory is finite. Eventually, it has to erase old information to make room for new. In 1961, a physicist named Rolf Landauer proved that erasing information is not free. Deleting a single bit dumps a tiny, unavoidable puff of heat into the surroundings. It generates entropy. And when you add up the entropy from all that forgetting, it exactly cancels the order the demon created. The second law survives, not because the sorting fails, but because thinking has a cost. Let that land. Information is physical. A memory has a temperature. The act of forgetting something warms the universe by a measurable amount. The demon wasn't beaten by muscle or friction. It was beaten by having to erase its own mind. Number 9. Zeno's Paradox. 2,500 years ago, a Greek philosopher named Zeno of Elea came up with an argument so simple and so infuriating that people are still chewing on it today. He claimed to prove that motion is impossible, that you can never actually get anywhere. Here's the famous version. The great hero Achilles, fastest runner alive, races a tortoise. Being sporting, he gives the tortoise a head start. Now, says Zeno, Achilles can never catch it. Why? To reach the tortoise, Achilles first has to get to where the tortoise started, but in the time it takes him to cover that distance, the tortoise has crawled a little further ahead. So now Achilles has to cover that new gap. But by the time he does, the tortoise has moved again. A little less this time, but it's moved. And again. And again. There are infinitely many of these gaps, each smaller than the last. And Zeno's point is that you can never finish an infinite number of steps. So Achilles closes in forever and never quite passes. Except, of course, he does. Anyone can outrun a tortoise. The conclusion is obviously wrong. The maddening part is explaining exactly why. The mathematical answer took 2,000 years to make rigorous, and it's this. An infinite number of things can add up to a finite total. The gaps shrink so fast, each roughly half the one before, that even though there are infinitely many of them, their sum is a normal, finite distance. Achilles crosses infinitely many shrinking intervals in a perfectly ordinary few seconds. The infinity is real, but it fits inside a finite space. And that, for a long time, was considered case closed. Calculus tamed the infinite sum, and Zeno became a historical curiosity, but here's the part that keeps it alive. Zeno's paradox quietly assumes that space and time can be divided forever, that between any 2 points there's always a smaller step. And physics is no longer sure that's true. Down at the very smallest scales, near what's called the Planck length, our theories start to break, and some physicists suspect that space and time may not be smooth at all, that they might come in tiny, indivisible chunks, like pixels. If that's right, then there is no infinite series of halfway points. There's a smallest possible step, and motion happens in the tiniest of jumps. Zeno was wrong about Achilles, but the question underneath his little riddle, whether reality is smooth or grainy, is one of the deepest open questions we have. 25 centuries later, the tortoise is still ahead. Number 8. Hilbert's Hotel. Imagine a hotel with an infinite number of rooms. Not a lot of rooms. Infinite. Room 1, Room 2, Room 3, going on forever with no last room. And tonight, the hotel is completely full. Every single one of those infinite rooms has a guest in it. A tired traveler walks in and asks for a room. The place is full. Infinitely full. What does the manager do? He gives the traveler a room. Easily. Here's the trick. He asks every current guest to move down one room. The person in room 1 moves to room 2. Room 2 moves to room 3. Everybody shifts over by 1. Since there's no last room, nobody gets pushed out the end. There is no end. And now room 1 is empty, and the new guest checks in. A full hotel, and there was always room. Already your brain should be filing a complaint. It gets worse. Now, an infinitely long bus pulls up, carrying infinitely many new guests, and every room is still occupied. No problem. The manager asks each guest to move to the room number that's double their current one. Room 1 goes to room 2. Room 2 goes to room 4. 3 goes to 6, and so on. Now every guest is in an even-numbered room. All the odd-numbered rooms, and there are infinitely many of those, are suddenly empty. The entire infinite bus load checks in. You can even handle infinitely many infinite buses arriving at once. There's a clever numbering scheme that fits them all. The hotel never fills up. It cannot fill up. This was dreamed up by the great mathematician David Hilbert in the 1920s. And it's not a puzzle about hotels. It's a window into what infinity actually is. And infinity does not behave like a number. With ordinary numbers, the whole is bigger than any part. Infinity laughs at that. An infinite set can be the exact same size as a piece of itself. Half the rooms, the even ones, are somehow just as numerous as all the rooms. That sounds like a contradiction, but it isn't. It's a rigorous, proven feature of how mathematicians handle the infinite, going back to the work of Georg Cantor, who first showed that some infinities are even bigger than others. Here's what stays with me. We use the word infinite casually, all the time. Infinite space, infinite possibilities. But almost nobody realizes that the moment you take infinity seriously, arithmetic itself stops working the way you trust it to. A full hotel with endless vacancy. That's not a trick. That's just what forever means. Number 7. The Banach-Tarski Paradox. This one is a proven mathematical theorem, and when you first understand what it says, your instinct will be that it must be a lie. It isn't. It says this. Take a solid ball, a sphere, like a billiard ball. You can cut it into a small number of pieces. Just 5 is enough. And then, without stretching or adding anything, using nothing but rotations and slides, reassemble those exact same pieces into 2 solid balls, each one identical to the one you started with. Same size, same density, same everything. 1 ball becomes 2, out of nothing. Volume doubles. And it is airtight mathematics. 2 Polish mathematicians, Stefan Banach and Alfred Tarski, published this in 1924. People sometimes summarize it by saying, you could chop up a pea and reassemble the pieces into an object the size of the sun. And that summary, absurd as it sounds, is fair. So how is this not insane? How does it not break the universe? The secret is in the pieces. These aren't clean slices, like cutting an orange. The pieces are infinitely intricate scatterings of individual points, dust so pathologically fragmented that they don't have a well-defined volume at all. You literally cannot ask, how much space does this piece take up? Because the question has no answer for shapes this strange. And when you're working with pieces that have no measurable volume, the normal rule that volume has to be conserved simply doesn't apply. There's nothing to conserve. To construct these ghostly pieces, the proof leans on a controversial tool called the axiom of choice, which lets you make infinitely many arbitrary selections all at once, with no rule for how. Some mathematicians are so bothered by results like this that they'd rather throw the axiom of choice out entirely. And here's the reassuring part, and also the strangest part. The reason you can't actually do this with a real billiard ball is that real matter is made of atoms. Atoms are not infinitely divisible. You eventually hit a smallest piece, and you can't keep cutting into that infinite dust. The paradox lives in pure mathematics, in a perfectly continuous, infinitely divisible space that reality only pretends to be. So Banach-Tarski isn't a claim about billiard balls. It's a warning. It's mathematics showing you that the smooth, continuous, infinitely divisible space we casually assume the world is made of allows things so bizarre they'd let you duplicate matter from nothing. Maybe reality isn't that kind of space at all, and the fact that you can't do this in your kitchen might be one of the deepest hints we have about what the universe is really made of. Number 6. The Bootstrap Paradox. Suppose time travel is possible. A lot of the trouble that follows involves someone changing the past. But there's a stranger kind of trouble, one where nothing gets changed at all, and it might be even harder to swallow. Here's a version. A music historian builds a time machine and travels back to visit a young Ludwig van Beethoven. She brings with her, as a gift, a printed copy of the complete symphonies. Beethoven, still early in his career, reads through them, is stunned by their beauty, and, over the following years, writes them all out and publishes them as his own. They become the symphonies we know. Now ask a simple question. Who composed the music? Beethoven didn't. He copied it from the book. But the book came from the future, where the music existed only because Beethoven published it. The historian didn't write it either. She just carried it back. Trace the origin of that music, and you go in a perfect circle, and you never, ever find a person who actually composed a single note. The music exists, but it was never created. It has no origin. It just is, looping around through time, causing itself. This is the Bootstrap Paradox, named from an old science fiction story about a man who pulls himself up by his own bootstraps. Sometimes it's called the ontological paradox, and here's what makes it so slippery. Unlike other time travel puzzles, Nothing here is contradictory. There's no logical crash, no moment where two facts collide. The loop is completely, seamlessly consistent. Beethoven gets the music, publishes it, it survives to the future, gets carried back. Beethoven gets the music. Round and round, forever, no problem. Nothing breaks, except your sense that things are supposed to come from somewhere. We take it as bedrock that every object, every idea, every piece of information had a beginning. Someone had the thought first, something caused it. The Bootstrap Paradox describes a situation, allowed in principle if backward time travel is real, where that's just not true. Information can exist in a closed loop with no source, created by no one, uncaused. Now, most physicists strongly suspect backward time travel isn't actually possible, precisely because it opens the door to things like this. But nobody has definitively ruled it out. The equations of general relativity, under certain extreme and exotic conditions, don't forbid loops in time. And if even one such loop is possible anywhere in the universe, then somewhere out there could be a thing, an object, a fact, a melody that no one ever made. It simply always was, chasing its own tail through eternity. Number 5, the Grandfather Paradox. This is the big one, the time travel paradox everyone knows, and it's worth looking at closely, because it might be telling us something profound about what the past actually is. The setup is brutal in its simplicity. You build a time machine and travel back to before your grandparents ever met, and you make sure they never do. Doesn't matter how. The result is the same. If they never meet, one of your parents is never born. If that parent is never born, neither are you. And if you were never born, you never grew up, never built the time machine, and never went back to keep them apart. But if you never went back, then nothing stopped them meeting. So they meet, your parent is born, you're born, you build the machine, you go back, and you stop them again. And around it goes, a loop that erases the very thing that starts it. It cannot happen, and it cannot not happen. So what gives? There are a few serious answers, and they're each stranger than the last. The first is the self-consistency principle, worked out by the physicist Igor Novikov. It says the universe simply does not allow inconsistent histories. Time travel might be possible, but any attempt to change the past is guaranteed to fail. Not by magic, but by ordinary bad luck stacked exactly high enough. The gun jams. You slip. You get the wrong house. Something every single time prevents the contradiction. In this picture, the universe doesn't forbid time travel. It forbids failure. You could go back, but you'd find yourself strangely, relentlessly unable to change a thing. The second answer is the many worlds idea. The moment you interfere, you don't rewrite your own past. You split off a new timeline, a parallel branch where those two people never met, and a different history unfolds. Your grandparents in your original world still met. You still exist. You've just visited a copy of the past that now goes its own way. No contradiction, because there are two timelines, not one. And in 2020, a pair of researchers in Australia worked through the mathematics and argued that events can always rearrange themselves to stay consistent, that the universe has, in a sense, enough flexibility to route around the paradox no matter what you do. Here's the thought I can't shake. Every one of these answers, in its own way, is telling you the past is not soft. It's not clay you can push around. Whether it's cosmic bad luck, or splitting worlds, or self-correcting math, the universe seems determined to protect what already happened. The past, it turns out, might defend itself. Number 4. The EPR Paradox. In 1935, Albert Einstein set out to prove that quantum mechanics was broken. He was the most famous scientist alive at the height of his powers, and he was convinced the theory had to be incomplete. So with two colleagues, Boris Podolsky and Nathan Rosen, he designed a thought experiment to expose its absurdity. Their three initials, EPR, gave it its name. Here's the idea. Quantum mechanics allows two particles to become entangled, linked in such a way that they share a single connected state. Now separate them. Send one to the far side of the room or the far side of the galaxy. It doesn't matter. According to the theory, neither particle has a definite property, say, which way it's spinning, until you measure it. The measurement is what forces an answer. But here's the catch that horrified Einstein. Because they're entangled, the instant you measure one particle and it snaps into a definite state, the other one, no matter how far away, instantly snaps into the matching state. Immediately. With no signal passing between them across any distance, faster than light could ever travel. Einstein found this ridiculous. He called it spooky action at a distance. To him it was obvious that the particles must have secretly had their properties all along, like a pair of gloves sealed in separate boxes, one left, one right. Open one box, you instantly know the other, but nothing spooky happened. The answer was just set in advance. Reality, he insisted, must work like that, and quantum mechanics was simply too dim to see the hidden details. For 30 years, it looked like an argument no one could settle. Then, in 1964, a physicist named John Bell found a way to actually test it. He worked out that if Einstein was right, and the particles carried hidden, preset answers, then certain measurements would have to obey a strict numerical limit. But if quantum mechanics was right, that limit would be violated. It was a way to ask the universe directly. Gloves and boxes, or spooky action. The experiments were done, refined over decades by John Clauser, Alan Aspect, Anton Zeilinger, closing every loophole. In 2022, the three of them won the Nobel Prize for it, and the verdict was total. Einstein was wrong. The particles do not carry hidden answers. The connection is real. Measure one, and the other responds, instantly, across any distance. The universe is non-local, woven together in a way that Einstein found unacceptable. And it does it right in front of us, on demand. The greatest physicist who ever lived bet against the strangeness of reality. And reality won. Number 3. The black hole information paradox. This is a war between the two greatest theories in all of physics. And as of right now, nobody is completely sure who wins. On one side, general relativity, Einstein's theory of gravity, which describes black holes. On the other, quantum mechanics, which describes everything small. Each is fantastically well tested. Each is trusted completely. And on this one question, they flatly contradict each other. Here's how the trap springs shut. In 1974, Stephen Hawking made a stunning discovery. Black holes are not perfectly black. Due to quantum effects right at their edge, they very slowly leak radiation. Over unimaginable spans of time, that leakage means a black hole shrinks and eventually evaporates away to nothing. Fine so far. But Hawking's own calculation showed that the radiation coming out is thermal, featureless, random. It carries no information about whatever fell into the black hole. Burn a book in a fire and, in principle, the smoke and ash still encode what was written if you could track every particle. But throw a book into a black hole and wait for it to evaporate. And according to Hawking, that information is gone, utterly erased, as if it never existed. And that is forbidden. One of the deepest rules of quantum mechanics is that information is never truly destroyed. The present always, in principle, contains a full record of the past. Hawking's black hole breaks that rule. So either general relativity is wrong about black holes, or quantum mechanics is wrong about information. Both cannot be right. For decades, this raged. And here's a detail I love. Hawking himself was so sure information was destroyed that he made a famous bet on it. He bet against the information surviving. In 2004, he conceded that bet, publicly changing his mind. Because the tide had turned. Most physicists now believe the information does survive, somehow encoded in that escaping radiation in a way Hawking's original calculation was too crude to capture. And in 2019, there was a real breakthrough. Using a set of tools with a strange name, the island rule, physicists managed to redo the calculation and get the answer quantum mechanics demands. The information gets out. The books are not erased. But, and this is a big but, they can show that the information survives without fully explaining how it physically escapes from behind the point of no return. The bookkeeping now works. The mechanism is still murky. So the paradox is cracked, but not closed. Somewhere in the death of a black hole is the key to uniting gravity and the quantum, the two halves of physics that refuse to speak to each other. We're closer than we've ever been, and we're still standing at the edge, looking in. Number 2, the Fermi Paradox. The whole thing started supposedly over lunch. In the summer of 1950, the physicist Enrico Fermi was walking to the cafeteria at Los Alamos with a few colleagues. They'd been joking about a cartoon involving flying saucers. The talk drifted to aliens, to whether interstellar travel might be possible. They sat down. And then, apparently out of nowhere, in the middle of lunch, Fermi asked a question that has haunted science ever since. Where is everybody? Here's the weight behind those 3 words. Our galaxy is enormous, hundreds of billions of stars, and it is old, over 13 billion years. We now know that planets are everywhere, that most stars have them. There has been an astonishing amount of time and an astonishing number of worlds for life to arise. And here's the kicker. Even if a civilization spread slowly, crawling from star to star at speeds we could imagine building today, the math says it would still colonize the entire galaxy in just a few million years. Against the age of the galaxy, a few million years is nothing. An afternoon. So the galaxy should be full. Every star visited, every world touched, the sky humming with signals, and ships, and the evidence of a billion-year-old civilization. Instead, we look up, and we listen, and there is nothing. Silence. No signals. No probes. No megastructures. No trace, anywhere, of anyone. The universe looks completely, eerily empty. That's the paradox. Everything we know says they should be here, and they're not. People have spent 70 years proposing answers, and every one of them is unsettling in its own way. Maybe life is just staggeringly rare, and we're alone. Maybe intelligence almost always destroys itself not long after it arises, and there's a graveyard of dead civilizations out there, and a warning in it for us. Maybe they're out there but deliberately silent, hiding, because announcing yourself to the cosmos is dangerous. Maybe they're so advanced we couldn't recognize them if we tried. We don't know. That's the honest answer. Every possibility is either lonely or frightening. And here's what gets me about the story. Fermi never wrote a single paper about it. He tossed the question out over lunch, and 4 years later, he was dead. He didn't solve it. He didn't even try. He just noticed the silence, said it out loud, and let it hang there. It's been hanging there ever since. Every clear night, over your head, is the biggest, quietest question we have ever asked. And so far, nothing has answered. Number 1, the Doomsday Argument. We end with a paradox that doesn't need a black hole or a rocket or a quantum particle. It only needs you, the fact that you exist, right now, reading this. That single fact, some very serious thinkers argue, lets you estimate how much time humanity has left. and the answer it whispers is not comforting. Here's the reasoning, and I want you to follow it slowly, because it sounds like a trick, and it might not be one. Think of every human being who will ever live, from the first of our kind to the very last, all lined up in the order they were born. You have a number in that line. Roughly, about 100 billion humans have been born before you. So your birth number is somewhere around 100 billion. Now here's the move. You have no special reason to think you're at some particular meaningful spot in that lineup. You're just a person. So treat your position as basically random, a ticket drawn from the whole span of human history, past and future. And if your number is random, then it's very unlikely you're in the first tiny sliver of everyone who will ever live. It's much more likely you're somewhere in the vast middle. But watch what that implies. If humanity were going to spread across the galaxy and last for millions of years, producing not 100 billion people, but 100 trillion, then you, sitting here this early, would be freakishly near the very beginning. One of the first unlucky few out of an enormous future crowd. And that, the argument says, is improbable. If you're a random human, you're probably not one of the first 1,000%, which means, statistically, the total number of humans who will ever live is probably not vastly larger than the number who already have. The future is likely not a trillion strong. It may be closer to the 100 billion we've already seen, which means, in the long run, we may not have nearly as much time as we like to imagine. This is called the Doomsday Argument. It was developed by the astrophysicist Brandon Carter and the philosopher John Leslie, and independently by another astrophysicist, Richard Gott, who published his version in 1993. And the thing that makes it so hard to wave away is that it uses no physics of catastrophe at all. No asteroid, no war, no plague. Just a single assumption that you are not special, that your place in the story is ordinary. People have argued about this for decades, and there are real objections about what counts as random, about who gets counted in the line. It may be wrong, but nobody has cleanly killed it. And that's the strange, quiet place we end up. Every other paradox tonight was out there, in the stars, in the equations, in the deep structure of space and time. This one is looking back at you. You wanted to know how long we have. It turns out you might be the only clue you need. Not a scientist, not a telescope. Just you, existing now. An ordinary point on a line whose end you cannot see, but can, perhaps, begin to guess. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.